Sina, who is with the Ewasm team, and his talk will be about how to improve user experience for light clients. Welcome, Sina.
Oh, it was on mute. Hello, everyone. This is Sina. I don't know what time zone you're in, but it's an evening here in Berlin. And you got to give me a minute to share my slides, and we'll jump right into it. I'm sorry, this is just going to take a few seconds.
No worries, take your time.
Yeah, Google is asking for a CAPTCHA. Okay. Can you guys see the slides?
That looks wonderful.
Okay, perfect. So yeah, this evening I wanted to talk to you guys about light clients, and this is a topic that I care about because my work on the protocol started with the JavaScript implementation of the EVM, and I really like it to become a light client in the browser one day. And so I decided to work on this topic. And I feel like this is a topic that's not being discussed as much recently, even though it has good synergies with stateless Ethereum and the recent discussions around client diversity. With light clients, we can have clients that don't have as much implementation complexity. They don't need to implement all the old hard fork logics. They have a simpler networking stack. And yeah, it's good to be able to have nodes running in the browser or on the mobile without relying on third-party services. So one of the light clients face multiple challenges. Although we have LES that's running, one of the main challenges that they face is that in order to have a light client, you need a light server, and the servers need to respond to requests from the clients. And currently, this is an interactive process. So my mobile has to send a request to the server saying, hey, give me this data. And this causes these servers to become easily overloaded. And therefore, although most of them are currently altruistic, we need complex incentivization schemes for them to work in scale. So the kind of the ideal scenario that I was imagining, and this was first expressed by others like TurboGeth team, is to have another sub network with mostly light clients, but some full nodes that just broadcast data, so that the light clients don't have to request data, but let's say a new block comes in, the full nodes broadcast the block itself and the stateless block witness, as well as a short proof that shows the total difficulty of that chain. And this will be the focus of our talk, so we'll talk more about that later on. And this allows the light clients to be able to follow the tip of the chain in a few seconds. And the amount of data that light clients will have to request from the servers would be minimized. So as I said, our focus here is determining the canonical chain. With that, I mean, let's say we have a couple of competing forks, and we want the light client to be able to safely detect which one is the correct one, the one that everybody is using. And currently, the way that this is done, so the most safe but also most demanding way of doing this is to simply download all of the headers from Genesis until the last block and verify all of them. And this would be just verifying the header, not executing the body itself. This is what the full nodes are doing, but for light clients, you don't really need to do this, especially when you consider that the total size of the block headers is somewhere between 5 and 8 gigabytes. So if you want to have a client on the mobile or a browser, this is already a non-starter. And the current LES protocol works around this by kind of hard coding some checkpoints in the client in the form of CHTs. And then you don't need to really verify the block headers from the beginning, but from the last checkpoint. But we want to see if we can kind of avoid this, having this hard-coded checkpoints. All right, so our design space is, I broke it into a simple spectrum. And these four items that you see are kind of what we will be discussing during this talk. We have full verification that is not complex at all in implementation wise, but it requires the most bandwidth of all. And then we have a hypothetical zero knowledge protocol. We have flight client, and we have EIP 2935 that is being discussed for Berlin, or the hard fork after that. So let's jump right into ZKP. This is a hypothetical approach. It's not being really suggested as being implemented in like ETH1, mainly because zero knowledge protocols are really complicated, and we want to avoid bringing them into consensus. So, but the approach would be that each block would come with a short zero knowledge proof that proves that there is a chain, like an unbroken chain of blocks from Genesis to this last block, and that the block headers of all of these blocks are valid according to the consensus rules. And it also tells us the total difficulty of the chain. And we use this total difficulty to be able to choose between forks. What I want you to take away from this approach is the ideal properties that we are looking for, and these are ideally short proofs. So for ZK snarks, this is definitely less than 1 kilobyte, and importantly, non-interactive proofs. So you don't need to communicate with the client, with the generating or the miner, to verify that. So somebody like a miner can produce this proof and just send it to everybody, and everybody can verify it on their own. And of course, security is important, and zero knowledge proofs have with very high probability good security. And now to the flight client, and this was a paper published in 2019, I think, by Benedikt Bunz, and it offers some good features. Like it offers short and non-interactive proofs of around 500 kilobytes to 2 megabytes. It depending on some configurations. I think this was 500 kilobytes was in their paper for 7 million blocks. It's secure with really high probability. It was recently activated on Zcash, and it's being built by default in some other blockchains, I think on Grin and Beam as well. And it can be configured to tolerate more or less dishonest mining power. But of course, flight client protocol needs some changes to be made in consensus. And it boils down to adding a new field to the block header. And this new field is the root of a tree that includes the block hash of all the blocks since Genesis. And the tree in question is not a normal Merkle tree. It's a customized Merkle mountain range. Let's call it the difficulty MMR. Just as a refresher, this is how a normal Merkle mountain range looks like. And the color of the leaves don't have a semantic meaning. That's just because here it's already autumn, so the leaves have changed their colors. And this is an append-only data structure. So, and here we have 15 leaves inserted from left to right. So you can see kind of that it turns into multiple binary trees next to each other. And it's very efficient. Insertions are very efficient in this data structure. And you get very short proofs when the leaf that you're interested in is very recent. So the older blocks would have longer proofs, but the more recent ones would have shorter proofs, which is perfect for our use case. And now in Flight Client, they've changed this MMR to include some additional metadata. And the more important ones are regarding difficulty and the time it took to produce that block and so on. And here you see like a really simple example of a difficulty MMR with a simplified difficulty MMR with 3 leaves. And you can see that the leaves have the block hash itself, but also, let me actually turn on the pointer. Yeah, so you can see that this leaf has a difficulty of 5, and this one has a difficulty of 7. And when you go up, then you add the difficulty to get a difficulty of 12. So this way you add the root of each of these trees, you have the total difficulty accumulated in all of those blocks, which is a great property. And this is used extensively in the protocol. Now, how do you use this tree to actually sync a light client? Let's say we have 2 competing forks. We have an honest miner who's advertising a total difficulty of 700, and we have a shady looking guy who's advertising a higher total difficulty of 1000. And the light client doesn't know which one is the canonical chain. So what it does is like first sorts them by total difficulty. So the one that has 1000, it will check it first, this fork first. And the gist of the protocol is just to do random sampling of the blocks. So you don't verify all of them, you check some of them randomly. And you can see that, okay, this fork, like this chain has forked off at this point here. And we're checking some of them, like if you see the ones that have a green circle around them, let's say we are checking those randomly. And in fact, we've checked 3, and one of them is an invalid block. So we caught you, Mr. Shady. And okay. So the core of Flight Client is in the sampling strategy. As you can imagine, just doing a uniform sampling won't be really efficient or sufficient. The goal of the sampling strategy is to maximize the chance of catching an invalid block, regardless of the adversary's strategy. Like whatever strategy they're using, we want to maximize the chance of finding if there's an invalid block in there. And the way it turns out is that it's like a probability distribution where we sample more from the end of the chain. Like we sample a few from the beginning, and as you go towards the end, we sample more and more. This is just because an attacker could fork later on to use the work that was accumulated by honest miners. And an important thing to note is that we're not sampling in the block number space. So we're not saying, let's say we have a chain of 10 million blocks. We're not saying, give me the block 5 million. Rather, we're saying, give me the block with half of the total work. And we can do this because in the Merkle Mountain range, we're storing that extra metadata that tells us the total difficulty of each subtree. The other point to consider is that each sampling step is independent. So they are not, so you don't have to like first get one block and then depending on whether it's valid or not, check another one. They're all independent. So what we can do is use the Fiat-Shamir heuristic to make this process non-interactive. And that's great because then the miner can just, when there's a new block, just produce a short proof of all these using some public source of randomness. For example, the parent block's hash. So it uses this parent block's hash to get a random seed and get the list of blocks that have to be included in the proof and send that to the like plans along with the necessary Merkle proofs in the Merkle-Mann range tree. Next, we have EIP 2935. And this is an EIP by Vitalik. And it's a much simpler change compared to FlyClient in terms of consensus complexity. And the difference is that we're not this time storing the Merkle-Mann range in the block header. Rather, we are using the existing Ethereum trie to store these block hashes. So as you probably know, we have let's say this is a block, and the block has a state root field, which is the root of the account trie. So what we do is like we hard code an address. We say this specific address is a special, like a system contract. Let's call it the history contract. And this has like storage slots like normal contracts. And in the storage slots of this account, we store the hashes of the blocks and the blocks since the hard fork, not since Genesis. This is an important distinction. So we're reusing a lot of the data structures that are already part of consensus, namely the Merkle-Patricia tree. So the motivations of this EIP were stated as like-client sync, what we're discussing now, but it's not limited to this. Neither this EIP nor FlyClient. They both are good for other purposes as well. Another one is, for example, like layer 2 state providing networks. Let's say clients like Get start pruning history. So you don't, as a new client, you don't have access to the older blocks. And when there's a commitment to the block hashes in the state, then what you can do is ask a third party to give you that block along with a proof so that you can be sure that this block is indeed the third block in the chain, let's say. And you can, this layer 2 solution can be incentivized as well. You can also use these for stateless witnesses because you have the block hash opcode, so block hashes of previous blocks need to be included in the witness. And here, so what we want to address here is if we can build a like-client sync protocol on top of this EIP, and we'll consider two approaches, two variants. One is very similar to FlyClient, and it's a random sampling approach. The other one is a Superblock approach, and Superblock, I'm borrowing the term from Nepopal, another like-client sync paper. So first, let's see what advantage does this EIP bring. Let's say we don't have the EIP 2935. Let's say right now. Why can't we do random sampling? The reason is that the like client doesn't know when it's asking for a random block, let's say block 7 million, it doesn't know that these blocks that he's asking for are actually chained together. The attacker could just give some random blocks that are not even part of a single chain. But committing to the whole chain in the state, it makes it harder for attackers to do something like this. But there are also some challenges in doing random sampling on top of this EIP. As you saw earlier in Fly Client, we query in the difficulty space. So we are asking, what is the block that has, let's say, half of the total work? And this is important because otherwise an attacker could create a long chain with many low difficulty blocks, but valid, like from proof of work point of view, and hide a few high difficulty but invalid blocks in the middle. And when you're randomly sampling, it's really hard to find them if you're sampling in the block number space. Again, because we're not using the MMR and we are stuck with the Merkle-Patricia tree, we can't do sub-range checks. So we can't say, let's say when we are verifying an old block, we can't really check that this old block is actually the tip of a chain that is a prefix of the bigger chain, that like the canonical chain. Again, with a Merkle-Patricia tree, this is a really inefficient thing to do. So we're kind of stuck with doing uniform sampling, and in order to if you want to have good security with uniform sampling, you need to sample a lot. So this means doing this approach either entails higher bandwidth requirements or it has lower security guarantees. So as an alternative to random sampling, Vitalik proposed an alternative, which here I'm calling Superblockbased Sync. And the intuition here is that, so as you might know, the blocks in Ethereum, they have a kind of a difficulty target, and a proof of work is valid. A proof of work solution is valid only if it's exceeding this target. And normally, most of the blocks, as you can see here, I have, so this red line here, let's say that's the target over time. And these blocks, they barely pass that target. But sometimes, by chance, some blocks have a much higher target. And there's a relation. So blocks that have 1,000 times more difficulty than the target are 1,000 times more rare. And so the idea is to use these really lucky blocks as a way of compressing the chain. And he estimates the proof sizes. So let's say the idea would be just send all of the lucky blocks that have 1,000 times more difficulty than the target as a way of showing that this chain is canonical, because an attacker with lower mining power cannot generate so many super blocks. And he so proof sizes of including all of these, Vitalik estimates them to be around 25 megabytes, and this includes all the super blocks, but also a few thousand blocks at the tip of the chain. And we might need to double this estimate because we also need to send the parent headers to be able to verify each block. So regarding security, NepoPow was advertised for constant difficulty chains. If the difficulty of a chain is constant over time, then an adversary with less than 50% mining power has a really low chance of being able to produce more super blocks. But in Ethereum, difficulty can be adjusted. It can be changed over time by 5% over time, each block maximum. So a sketch for an attack could be that the attacker tries to bring down the difficulty so that they can produce more superblocks. But this can be easily avoided by modifying the fork choice rule. At the tip of the chain, as I mentioned before, so these blocks that have 1,000 times more difficulty, they are kind of rare. So it could be that the last few thousand blocks don't have any of these super blocks. So we have two options: either send all of the blocks after the last super block as part of the proof. Another one is to send super blocks of lower degrees or lower levels. Let's say blocks that have 500 times the difficulty or 100 times, and so on. So in this talk, we saw all the spectrum from full verification to zero knowledge proofs. But I think in the middle, between full verification and ZKPs, we can find some good middle ground. Fly client has good features. It has multiple use cases, but it has somewhat higher consensus complexity. EIP 2935 has lower complexity. It might need higher bandwidth. The algorithms that we discussed haven't been formally analyzed, so this is something that has to be done. But it might suffice to replace CHTs. And in future, what we plan to do is come up with more detailed algorithm for the superblock approach and prototype them, prototype both the superblock approach and the flight client approach, and compare them quantitatively for more exact comparison. So that was it. There is also a text format for the same presentation. You can find the link on this page. And otherwise, if you have questions, I'll be available on the chat or on Twitter. Feel free to reach out, and I'll be happy to take any questions.
Amazing. Thank you so much, Sina. I think we have time to take one more question from the chat, and I believe there was also some more discussion going on, which you can then maybe take offline after the talk. But one question that we want to ask is from TRX314. What are the implications of this architecture in terms of privacy for the users of the Light client?
I don't believe there should be a negative effect on privacy for any of these approaches. In fact, it might be better because we're trying to reduce this request response mechanism. So when you request something, when you request a block, that's an information being leaked to the full node. But when you make it broadcast only, then the full node doesn't know who's getting this message, this proof, and what they're doing with it. So I believe it might be better for privacy. But yeah, I'll be happy to think more about the privacy consequences.
Okay, amazing. Yeah, I think there was some discussion going on in the chat also, so maybe you want to have a look, and then we will wrap this up here. Thanks so much for joining us and giving.
Thank you, Francine.